We proceed mathematical induction exercise 4.1. Let us see question number 2. We have to prove by mathematical induction. The question is 1 raised to the power 3 plus 2 raised to the power 3 plus 3 raised to the power 3 plus dash dash and n raised to the power 3 equals to n into n plus 1 upon 2 the whole square. So we have to prove this statement by mathematical induction, and the procedure to prove by mathematical induction: first we prove that the statement is true for n equals to 1. So let Pn such that 1 cube plus 2 cube plus 3 cube plus dash dash up to n cube equals to n into n plus 1 upon 2 the whole square. So for n equals to 1, on the LHS at the place of n we put 1. So we get for n equals to 1, LHS is 1. And for n equals to 1, RHS is found by putting the value of n in the right hand side. So 1 into 1 plus 1, 2. So RHS will become 1 into 2 upon 2 the whole square. 2 and 2 cancelled and 1 the whole square. It comes 1. So it is true. It is true for, we will write it is true for n equals to 1. Or we can also write Pn is true for n plus 1. Also we can write Pn is true for n equals to 1. Then in the next step, we suppose let Pn is true for n equals to k. For the next step, we suppose that Pn is true for n equals to k, and we put everywhere at the place of n as k. So it becomes 1 cube plus 2 cube plus 3 cube plus dash dash plus k cube equals to k into k plus 1 upon 2 the whole square, and name it first number equation. For n equals to k, we put the value of n equals to k everywhere. Now to prove, in the third step, to prove it is true for n equals to k plus 1. In the third step, we write to prove it is true for n equals to k plus 1. So for k plus 1 on the LHS, first we write the term up to k, means 1 cube plus 2 cube plus 3 cube plus dash dash k cube. This is a term up to k, and for k plus 1 we will write here plus k plus 1 the whole cube. At the place of n, we will write k plus 1. For writing n equals to k plus 1. And on the right hand side, at the place of n, we will put k plus 1. On the right side, at the place of n, we will write k plus 1. So this becomes k plus 1, then it comes k plus 1 plus 1 means k plus 2 upon 2 the whole square. In this step, we will prove that LHS is equals to RHS. And if it is true for n equals to k plus 1, then it must be true for n equals to k. So we will prove this statement LHS equals to RHS. So here we write LHS, and that is 1 cube plus 2 cube plus 3 cube plus dash dash k cube and plus k plus 1 the whole cube. We write the term containing LHS. Now up to the place k cube from first number equation up to the term 1 cube plus 2 cube plus 3 cube dash dash plus k cube up to this term, at the place of this we can write k into k plus 1 by 2 the whole square. So here we write k into k plus 1 upon 2 the whole square. The whole square, and this term would be written as it is plus k plus 1 the whole cube. K plus 1 the whole cube. Now we proceed. So we remove the bracket. So it becomes k square and k plus 1 the whole square upon 2 the whole square, we get 4, and plus k plus 1 the whole cube. From these two terms, we take common as k plus 1 the whole square. So we take common k plus 1 the whole square. It remains k square upon 4 plus k plus 1. Then k plus 1 the whole square, and by taking LCM 4, we get k square plus 4k and plus 4. So this expression can be written as, this would be written as it is k plus 1 the whole square, and this can be written as k plus 2 the whole square upon 4. And the entire term can be written as, in a single square, k plus 1 into k plus 2 upon 2 the whole square, and that is RHS. That is RHS. So we will write that it is true for, or Pn is true for n equals to k plus 1, hence it will also be true for n equals to k. Hence it is also true for n equals to k, and also for all real numbers. For all real numbers. So in the very first we proved that the Pn is true for n equals to 1. We put the value of n equals to 1 on both the sides, LHS and RHS. In the next step, we suppose that this statement is true for n equals to k, and at the place of n we write k, on both the sides, LHS and RHS. Then we prove that it is true for n equals to k plus 1. So after k, we will write the term containing k plus 1, and on the right side at the place of n, we placed k plus 1. Then we solve the RHS and we solve the LHS to get the RHS. And if it has been proved that it is true for n equals to k plus 1, hence it is true for n equals to k and also for all real numbers. Next, question number 3. One plus 1 upon 1 plus 2, 1 plus 1 upon 1 plus 2 plus 1 upon 1 plus 2 plus 3 plus dash dash 1 upon 1 plus 2 plus 3 plus dash dash up to n equals to 2n upon n plus 1 equals to 2n upon n plus 1. So in the first step, we write Pn such that 1 plus 1 upon 1 plus 2 plus 1 upon 1 plus 2 plus 3, and the last term 1 upon, this is 1 plus 2 plus 3 plus n. This is the sum to n terms, and formula for sum to n terms is n into n plus 1 by 2. We know that sum of n terms 1 plus 2 plus 3 plus n is equals to n into n plus 1 by 2. So at the place of sum of first natural number, we can write n into n plus 1 by 2. So here we write n into n plus 1 by 2, and this is equals to 2n upon n plus 1. Then it would be written Pn such that 1 plus 1 upon 1 plus 2 plus 1 upon 1 plus 2 plus 3 plus dash dash, and this can be written as 2 upon n into n plus 1 equals to 2n upon n plus 1. Now, in the first step, we make it true for n equals to 1. So here we write for n equals to 1, LHS, in the last term we put the value of n equals to 1. So we get 2 upon 1 into 1 plus 1, that is 2 upon 1 into 2, and which we get 1. So LHS comes to be 1. And in the RHS, also we put n equals to 1. So we get 2 into 1 upon 1 plus 1, 2. And RHS also comes to be 1. So we will write that Pn is true for n equals to 1. Pn is true for n equals to 1. This completes the first step. Now we suppose that The statement is true for n equals to k. So we write let it is true for n equals to k. And at the place of n, we will write k. So 1 plus 1 upon 1 plus 2 plus 1 upon 1 plus 2 plus 3 plus dash dash 2 upon, at the place of n we will write k, 2 upon k into k plus 1 equals to 2k upon k plus 1 and name it first number equation. Now for the third step, we will write to proof it is true for n equals to k plus 1. And for writing the term up to k plus 1, first we will write the term up to k term. So we write here as it is 1 plus 1 upon 1 plus 2 plus 1 upon 1 plus 2 plus 3 plus 2 upon k into k plus 1. This is the term up to k term. And for k plus 1, we replace k by k plus 1. So it becomes 2 upon, at the place of k, we will write k plus 1. Here again at the place of k, we will write k plus 1. Then it becomes k plus 1 plus 1, means k plus 2. And on the right side also we will write k plus 1 at the place of k. So 2 into k plus 1, here k plus 1 plus 1, we get k plus 2. Now in this step we have to prove that LHS equals to RHS. So we solve LHS, and for LHS, up to the term 2 upon k into k plus 1. From first, we can write till up to this, we can write 2k upon k plus 1. We will write 2k upon k plus 1 for 1 upon 1 plus 1 upon 1 plus 2 plus dash dash 2 upon k into k plus 1. So first number equation, from first number equation, we can write 2k upon k plus 1, and this would be written as it is, plus 2 upon k plus 1 and k plus 2. And from these two terms, we take common. So 2 upon k plus 1 is the common from both the terms. Here we get k plus 1 upon k plus 2. 2 upon k plus 1 we have taken common, here it remains k, and in the next step it remains 1 upon k plus 2. So 2 upon k plus 1, by taking LCM k plus 2, we get k into k plus 2 and plus 1. Then 2 upon k plus 1. Remove the bracket. So k square plus 2k plus 1 upon k plus 2. So 2 upon k plus 1. And this it can be written as k plus 1 the whole square upon k plus 2. 1 times k plus 1 cancel, and it comes 2 into k plus 1 upon k plus 2, which is RHS. So we proved that LHS equals to RHS. So it is true for n equals to k plus 1, and therefore it will also true for n equals to k. Hence it will, it must be true for n equals to k and also for n belongs to natural number. All natural number, this statement is true. Now question number 4. One into two into three. 1 into 2 into 3 plus 2 into 3 into 4 plus dash dash n into n plus 1 into n plus 2 equals to n into n plus 1 into n plus 2 into n plus 3 into n plus 4 upon 4. N into n plus 1, n plus 2, n plus 3 upon 4. This we have to prove. So for the first step, first we write let Pn such that 1 into 2 into 3 plus 2 into 3 into 4 plus dash dash n into n plus 1 into n plus 2, the last term, and which is equals to n into n plus 1 into n plus 2 into n plus 3 and upon 4. So in the first step, we put for n equals to 1, and for n equals to 1, LHS. In the last term, we put the value of n equals to 1. So 1 into 1 plus 1, 2 into 1 plus 2, 3. So we get LHS equals to 6. And for RHS, in the RHS, we put n equals to 1. So 1 into 1 plus 1, 2 into 3 into 4 upon 4. 4 and 4 cancelled, and we get 3 into 2, 6. So we'll write for n equals to 1, LHS equals to RHS. Therefore, it is true, or Pn is true for n equals to 1. Pn is true for n equals to 1, because for n equals to 1, LHS is equals to RHS. Now we suppose let Pn is true for n equals to k. So at the place of n on the both sides, we put k. So 1 into 2 into 3 plus 2 into 3 into 4 plus dash dash k into k plus 1 into k plus 2 equals to k into k plus 1 into k plus 2 into k plus 3 upon 4 and name it first number equation. Then in the third step we will write to prove it is true for n equals to k plus 1, and at the place of first we write the term up to k. So 1 into 2 into 3 plus 2 into 3 into 4 plus k into k plus 1 into k plus 2. This is the term up to k term. Then we have to write the term k plus 1. So at the place of k, we will place k plus 1. So this becomes k plus 1. It comes k plus 2 and k plus 3 equals to, at the place of k we replace by k plus 1, so it gives k plus 1 into k plus 2, k plus 3, k plus 4 upon 4. Now we solve LHS. So up to the term k from first number equation up to this term we can write k into k plus 1 into k plus 2 into k plus 3 upon 4, and this term would be written as it is. So plus k plus 1 into k plus 2 into k plus 3. Now we proceed this. So we take common. So from these two terms, k plus 1, k plus 2, k plus 3 is taken common. K plus 1, k plus 2 and k plus 3 is taken common. So here we get k by 4 plus 1. Here we get 1 and k plus 1 into k plus 2 into k plus 3. By taking LCM, we get k plus 4 upon 4, which is RHS. So after solving, we get the RHS. So it is true for n equals to k plus 1. Hence, it must be true for n equals to k and also for n belongs to capital N. It is also true for all natural numbers. N belongs to N. So in all the questions, there is common step. In the first step, we prove it is true for n equals to 1 by putting the value of n on both the sides. On the left side, in the last term, we put n equals to 1, we get 6. And on the RHS, when you put n equals to 1, we get 6. So since for n equals to 1, LHS equals to RHS, so we'll write Pn is true for n equals to 1. For the next step, let Pn is true for n equals to k. So at the place of n, we will write k. Then we write that let to prove it is true for n equals to k plus 1. So for writing the term up to k plus 1, first we write the term up to k. Then for k plus 1, at the place of k, we write k plus 1. So it becomes k plus 1, k plus 2 and k plus 3. And on the right side also, k is replaced by k plus 1. Then we get k plus 1, k plus 2, k plus 3, k plus 4. And we have to prove in this step, in the third step, LHS equals to RHS. So we solve the LHS, and up to this term we will write from first number equation this value and this would be written as it is. Then by taking common and solving we get the RHS. So it is true for n equals to k plus 1. Therefore it must be true for n equals to k and also for all natural numbers.